Hello everyone, my name is Zhijian, and today I'm going to present our work, Personalizing Head-Related Transfer Functions for Earables. This is a joint work with my advisor Ramit, and we are from University of Illinois at Urbana-Champaign. Imagine that you are wearing earphones, and you hear a voice that says, "Hello, please come this way." Can you tell if the sound is real or virtual? With today's earphones, you easily can. But is it possible to make the virtual sound indistinguishable with the real one? Or in other words, can we fool the brain so that it cannot tell the difference? This paper aims to design a filter such that when it is applied on the original sound source signal, it can trick the brain to believe that the virtual sound from the earphone is actually the actual sound. And we call this filter head-related transfer function, or HRTF. HRTF research began as early as the 1960s. People started to use artificially created head to understand the human's head and ears effect on the sound. But up to now, HRTF design is still a challenging problem. So why is HRTF design such a challenging problem? Let's try to understand. So first, we need to understand how the sound bends or diffracts around your cheek and face. And second, we need to understand how the real signal bounces inside your ear pinna before it arrives at the eardrum. And these two aspects combined depict the HRTF at any given angle theta. If the earbud can learn your personalized HRTF, then the task of fooling your brain is actually easy. We essentially need to pass the original sound signal through the personalized HRTF filter, and then a realistic spatial audio can be created. And this can enable a lot of applications. For example, spatial audio-based navigation. Let's imagine an acoustic augmented reality scenario where the user is at the airport and trying to find her gate. We can play a follow me to your gate sound from the earphone using virtual spatial audio. And then the user can basically follow the sound and reach the destination. Of course, personalized HRTF is also very useful in VR gaming when we want to render different spatially located sound sources. Or even during virtual meetings, we can add 360-degree audio so that people can have a spatial feeling as if the other attendees in the meeting are just sitting around. However, it is extremely difficult to understand how your head and ear affect the sound. So let's look at how HRTF measurement is being performed today. Actually, it needs to be done in very controlled settings. A user is asked to sit in a large acoustic chamber and wear in-ear microphones. A large rotating speaker array can then simulate the sound effect of a sound source at any given angle. And in this way, HRTFs can be estimated. This is, of course, very difficult to obtain. So this means the spatial audio products we see on the market these days are actually using the generic HRTF. But generic HRTF is not optimal. And to understand how much suboptimal the generic HRTF is, we did our experiment. So we passed the original sound signal through two filters. The first one is the generic HRTF filter, and the second one is a personalized HRTF filter. And we ask a user to identify the sound direction in these two cases. And this direction is the ground truth sound direction. And this is the user's perceived direction using a generic HRTF. And this is the perceived direction using the personalized HRTF. And we can see that generic HRTF leads to as large as 60 degrees externalization error. So it is obviously not good enough. Then the natural question is that, can we personalize HRTF without acoustic chambers? So actually, previous researchers have used 3D scan to capture the shape of the user's head and ear. And then they will perform acoustic simulation or machine learning-based approach on the 3D scan result. And in this way, they can obtain the HRTF. This is better than acoustic chamber, but some material properties like the skin and the hair properties is still very difficult to estimate. So this paper asks, can we build a system that allows easy personalized HRTF estimation at home? And we present our system Uniq. Here is the basic idea for Uniq. We will use the smartphone as a transmitter and in-ear microphone as receiver. And HRTF is estimated by asking the user to rotate the phone around the head. And the remaining slides are organized as the following. I will first talk about Uniq system sketch, and then I will give intuition about two technical parts, namely the phone localization part, as well as the near to far field conversion part. And finally, I'll talk about the implementation and evaluation. Then let's look at Uniq system sketch. We use smartphone as a transmitter, and smartphone transmits a known source signal S. And we use two in-ear microphones as receiver, and the two in-ear microphones receive signals R. We ask the user to move the phone, and IMU records motion. Then because we know the source signal S, and we also know the received signal R on both of these ears, then we can essentially estimate acoustic channel H for the left and right ear, HL and HR. And we also perform phone localization using phone IMU and in-ear microphone sensor fusion. Then if we have the precise phone location, we essentially have the near-field HRTF. Why? This is because near-field HRTF is essentially a one-to-one mapping between the phone location and the acoustic channel HL and HR. And finally, we will focus on near to far field HRTF conversion. This is because near field HRTF is not enough, because in a lot of cases, we want to create the effect for the far field sound, as shown in the grid head above in this slide where the sound source is far away. So then I will talk about the intuition of phone localization and near to far field conversion part. Let's first start with the phone localization part. So our goal is that as the user rotates the phone around the head, we want to localize each phone location at each time instance. So let's first look at a simple case. Assume we know the distance between microphones and there is no head between the microphones. Then localization is straightforward because we can essentially get the acoustic time of flight between the smartphone and the in-ear microphones. And this can translate to the distance, DIL and DIR. And then we can just perform a simple transliteration and the phone location can be estimated. But what if when there is a head in between? Then signal actually diffracts around the head instead of penetrating the head. So this means we need to model the diffractions to understand how the signal propagates. But to model the diffraction, we need head size and head shape, which we don't know for now. So what are we going to do? We propose a diffraction-aware sensor fusion algorithm. And the idea is the following. So we ask the user to face the phone towards the center of the head. This means the IMU measured angle theta I can actually translate to the phone polar angle alpha I. And if we also model diffraction-based trajectorization, then we can localize the phone location as PI, and PI can also give us a polar angle alpha I measurement. And these 2 points make the system overdetermined and brings us opportunity to jointly solve for the head shape and the phone location. And in this way, we can estimate where the phone is in each time instance. And there are more details in the paper about this diffraction-aware sensor fusion algorithm. And we now have the phone location estimated. By mapping the phone location with the acoustic channel, we get the near-field HRTF. And we can see that the near-field HRTF is actually coming from a point source. But in most of the cases, we will need far-field HRTF. And far-field HRTF is coming from parallel lines. And so I will talk about our next module, which is near to far-field HRTF conversion. So our goal is that we want to synthesize the far-field HRTF at angle theta using the near-field HRTF measurements that we have on the trajectory A. So our intuition is that far-field HRTF is actually a recombination of different rays for near-field HRTF at different locations. So I have plotted 3 points, x1, x2, and x3 here. So if we want to synthesize the far-field HRTF, we essentially want to pull out these parallel rays from these points, and then we combine these parallel rays together. This is essentially the far-field HRTF at angle theta. And the decomposition for the near-field HRTF is actually a very challenging problem. And I will not go into the details here, but basically we perform decomposition of the near-field HRTF and then recombine them to understand the far-field HRTF. And we now have the far-field HRTF estimated. So we pass any sound source signal that we want to render through the Uniq personalized HRTF filter. And in this way, we can create a realistic spatial audio for any given user. We implement Uniq on commercial off-the-shelf mobile devices, including a smartphone, speaker, and in-ear microphone. And we evaluate on the correlation between the estimated and ground truth HRTF. And let me first show the baseline result. This is the correlation between the generic HRTF and the ground truth HRTF. We can see that the correlation is low. And this is the result for correlation between Uniq estimated HRTF and the ground truth HRTF. And we can see that Uniq generates HRTF 1.8 times more accurate than the generic HRTF. There's also discussions about how we use our Uniq estimated HRTF to better understand the real-world sound incoming direction. So for more details, please read our paper, and thanks for listening.